should work. This time I even brought my pen, so I can do stuff. See, I can learn. Couple of announcements. Next week we'll have the first quiz. Some of you wondered regarding the details, the depth, and the difficulties of the quiz. The quiz overall, there's going to be 3 quizzes. The quiz will be 10% of your grade. The goal of the quiz is not to be as hard as possible, but more to check your general understanding of the material. So my suggestion would be to simply read the chapters in the book, go through the slides, get to know the main concept, and we'll ask you a couple of questions on the general topics of the lecture so far. The first quiz will be on the basics, so this is mostly just background information, types of bugs, different kinds of security policies, threat modeling, and so on. This will be a Moodle quiz of 30 minutes, and I am very much aware that you have a lot of quizzes scheduled at the same time. I don't want to increase your scheduling burden and make it super hard for you to find or like do 2 quizzes at the same time even. So what we'll do is we'll give you 24 hours to do the quiz of 30 minutes. It will just open next week after the class, and then you have 24 hours to do the quiz. This should give you sufficient time and flexibility to do the quiz at any point in time. I think it's a bit unfair if you have to like do 3 quizzes in 1 hour. There's no way for you to prepare or schedule or do anything for that. So I will be giving you 24 hours. This should give you at least, it's not perfect, but it should give you at least a little bit of flexibility to figure out when to do the quiz. The quizzes work in a way that as soon as you start, the timer starts running, and then you have 30 minutes. I usually ask for feedback along with the quizzes as well. So there's a couple of boxes with open text feedback where you can give comments about the course and the class and what I can do better. I do listen to feedback, so please feel free to share openly and freely. I did hear the complaint last year that the time was not enough to actually provide feedback, so I'll be doing two quizzes, like one for the grade and another one just to do feedback. I would really appreciate if you give me a quick update on how you perceive the course to be going, if there are any kind of issues that you're having, if there's anything that wasn't explained clearly, and so on. In earlier times, I did this weekly, with weekly quizzes, but then students complained that there were too many quizzes, so now we have 3 quizzes, and it's kind of hard to find a balance, right? And when listening to feedback, I'm trying to optimize across what you are saying and what previous generations of you have said. And it's a somewhat over-constrained problem. I'm trying to make this better and find a mostly satisfying solution, or a solution that is mostly sat. But yeah, there's constraints. But do let me know what issues you perceive with the labs, with the quizzes, with the slides, with the course, and so on, with the book and whatnot, and we'll try to improve and make this better. We're in this together, and we'll try to make this a fun experience for all of us. Sounds good? Cool. Questions, comments, concerns? Okay, let's get started. Today we'll talk about security policies. This is where we leave some of the introduction behind us, we leave some of the more general stuff behind us. We're going to talk about some security policies and also implementation of security policies. In this class, or today, you should learn about the different core security policies. We've talked about them a little bit before, but mostly in passing, so I just mentioned the different policies, so you should have at least heard of them. Today we're going to define them a little bit more deeply and go into figuring out some of the differences and the constraints when you're implementing them. So if you're putting your system developer hat on, you can start of thinking how to implement them or what are the necessary requirements for you to implement them, and then figuring out what the trade-offs or potential trade-offs are. We also will try to understand how memory safety and type safety apply to low-level programming languages. The labs are in C and C++. Right? These languages don't necessarily have memory and type safety, or they assume that memory and type safety is enforced by the programmer and not by the runtime system or the language or anything like that. So we'll have to we'll discuss how these the lack of these policies or enforcement of these policies affects the programs or applications written in these languages. And the goal is also to give examples of how these policies can be violated, like what would be a potential bug of this kind or that kind, what are the differences between the bugs, and also to understand what some of the trade-offs are. As always, feel free to ask questions as we go through the slides and through the material. Cool. What is a security policy? Well, a policy is a deliberate system of principles to guide decisions and achieve rational outcomes. A policy is a statement of intent and is implemented as a procedure or protocol. Right? So let's unpack this statement a bit. This is the definition that I took from Wikipedia, but you'll find similar definitions in other places. So a policy is it's a document, it's a form, it's a specification that tells us how we can decide, what we decide on, and the context in which we decide. It also gives us a hint of how this could be implemented. So the mechanism that then implements a given policy is driven by the policy specification, right? So a policy is this set of overarching principles that allow us to do follow-up decisions, and we can then decide, hey, memory safety is a policy, a security policy, it is violated through this, or that, or it is enforced through this, or that. And we'll give examples as we go on. The first policy we talk about is isolation. And isolation is the process or fact of isolating or being isolated. Any two components are isolated if their interactions are restricted. Now, what could components be? Right? Components could be, if you think about isolation, could be two processes. And we're talking about process isolation. Right? Two processes should be isolated from each other and should only be interacting with each other through a trusted third party that is an intermediary. And in this case, for processes, the intermediary is the operating system. So the operating system restricts how any two processes can interact with each other, even if the processes are from the same user. So if you bring back the details from your operating system class, you'll remember that, hey, the process abstraction is this virtual abstraction that allows us to group complex tasks into separate entities, and the operating system controls how to switch from one process to another and how two different processes can interact with each other. This interaction happens through a well-defined API that is under the control of the operating system. So a process may execute system calls and thereby asking the third party to interact with this other party. One example of a set of system calls would be inter-process communication. So you're asking another process to, for example, send a message to that process or receive a message from that process. It could also be opening a pipe, right, where you're reading through and writing through a pipe to communicate with another process. It could also be shared memory, right? So you're asking the operating system to set up a memory space, which is a view into the other process's memory space, right? So it would be like a window into the address space of the other process, where when you write, the other process sees as well. This is still isolation because you're using the API to set up this window into the other process's address space. So you cannot just do this on your own, or a process cannot do this on its own. It has to ask the operating system for permission to open up this window. And in the end, this is the mechanism that makes this performant. Simply opening a window into the other process's address space can be really, really fast because you're no longer bound through round trips through the kernel and back, but you can simply write to memory and the other process can simply read. What would be other examples of isolation in a computer, on a computer? Yeah?
Would be a browser tab.
A browser tab, yes. Different browser tabs should be isolated from each other. And there the browser ensures, like even if you think a couple of years back, everything was being run in one single process with multiple threads, the browser ensures separation and isolation between the individual browser tabs. Now it's often individual processes relying on the process abstraction as a somewhat defense in depth, where you have to go through the browser API and then through the operating system API to actually interact. Good example. What else? Yeah.
System calls?
That would be the process abstraction, right? System calls are already the same, right?
Of a virtual machine?
Virtual machine, yes. And there the VMM would control a set of VMs. What else? Yeah.
You can isolate things using the network, so setting up a virtual network such that the things are separate or even physically separate.
VLAN. Yeah, virtual networks. We are going deeper down the stack. What else? Yeah.
You can put your computer in the basement and not connect it to anything.
Physical separation, yes. Different server centers. Right, so we're pretty much down on the lowest level of the stack. Yeah. One more note to the VLANs. There can also be different entities, right? If you do have a network, different computers are separated and are interacting through through sending messages on the shared bus or shared network. If you look at this, any kind of bus isolates different components. So, for example, different kind of PCI devices on the same bus or so on, right? But this is fairly low level. Here we'll focus mostly on the software side of things and look at how we can implement this in software. Cool. Least privilege as the next example. Least privilege ensures that each component has the minimum amount of privileges to function. If any privilege is removed, the component stops to function. So an example here could be the system call policy, which restricts any kind of system calls and parameters that can be used, and like the operating system could check the system call policy accordingly. So again, we have a trusted third party that ensures that a policy is being enforced. And this will come back again and again here, right? A trusted third party makes enforcing policies much, much, much easier. And the trusted third party can be in software as the operating system, which can implement more heavyweight checks, or it can be in hardware, right? For example, if you look at SGX or other kind of secure enclaves that allow some form of separation. For least privilege, we had the example as well of browser tabs and the Chrome render process, which, if you remember, the render process is this large, complex beast that parses HTML files, CSS files, and everything else, runs a bunch of JavaScript, exposes APIs, and this is usually the most buggy part of any browser. This is why it has been isolated, separated, and these privileges being enforced to ensure that, hey, there's no unintended interactions between the systems. Least privilege here is enforced through seccomp. So seccomp is the mechanism. And the policy implemented on top of this is what is done by the Chrome browser. Do you remember what system calls seccomp allows in its minimal form? We had that 2 weeks ago, right? What's the minimum set of system calls? In the back? Exit, read, write, what else? Say again? Sig return and close. And secret. Okay, these 5 system calls are all that that is necessary. What do we need to ensure? What do we need to ensure to make it actually work? We need to set up before we start. Set up carefully. Right, before we start with before we start enforcing these privileges, we have to make sure that we set up the environment correctly. Right, as soon as we start the seccomp sandbox, we can no longer execute any other system calls from this process, and no other process can interact with this process. So how would you interact with such a process? How can you do things in this sandbox? Computation by itself is only useful if you can interact with the environment, right? So you need to be able to do something. You need to signal the outside somehow, and just computing in a busy loop and making the fan spin faster is not a good signal to transfer data outside of your sandbox. In the back.
Writing into one of the files that the process is allowed to access.
You can write into one of the files that the process is allowed to access, that the process is already opened. Right? Which means, as part of the policy, as part of the setup process, you have to open all the file descriptors that you actually need. Right? So you're setting up all the necessary pipes and file descriptors and whatnot that you need throughout this the execution of this process or of this sandbox, and make sure that the sandbox can actually interact with it. What does Chrome do? Right? Chrome sets up the 2 file descriptors, one for reading, one for writing, allowing it to transfer messages back and forth. So you have a channel, you have a communication channel. And then through this channel you can enforce a given API that whenever the render process tries to do something, it just writes a request. Think of this as an object that encapsulates a remote procedure call or an API call. That is being marshaled and sent to the other side. The other side reads this, interprets it, and makes sure that the request is reasonable, and then returns the data back. Right. So the mechanism enforces least privileges, but requires that it is being set up correctly in advance. So you need to have this other process that checks and exposes the given API and make sure that you can send data back and forth. Question? Yes.
Have there been cases where, for example, let's say you do something stupid and you pass shell commands through this API and you just run them? That would be a bit foolish. So are there cases where
yes,
the interpreter outside gives a much too permissive sort of RPC kind of system to
so the question was like if there have been bugs on the other end, or if I paraphrase it, how to escape this sandbox, right? And the sandbox is not perfect, right? This sandbox or least privilege ensures that the system through the SecCom sandbox can simply interact with the other end through the well-defined API. There's still other kind of issues that can happen if it's not if the API is not well designed. If the API has bugs, if the API has other issues, then this can be used to escape the sandbox. Right, so sandbox is a combination of compartmentalization and least privilege. We'll get to compartmentalization on the next slide. Right, so the least privilege is just like there can be bugs in least privilege, and the bugs can then be used to escape. Let's quickly move to compartmentalization, and then I'll follow up a bit on the question how to escape. Compartmentalization is again the policy as a general technique of separating two or more parts of a system to prevent malfunctions from spreading between them. And the sandbox here is a good example that requires, like if you want to implement least privileges as a sandbox, you need to have compartmentalization. Otherwise, without compartmentalization, the system could just ask for more privileges. So it requires a combination of isolation and least privilege. You need to separate the system, you need to break it up and make sure that it cannot interact with the rest of the system. So you require a strong policy to contain faults to single compartments or single components. And examples here are Qmail that uses a process and Unix user ID system to separate and ensure compartmentalization, or the Chromium render process that communicates through this well-defined, very narrow API to make sure that it cannot do any harm. The Chromium render process, the advantage of it is that it even restricts the kernel attack surface. Right? With Qmail, you have the potential disadvantage that any of these processes can execute any kernel system call that it has available. Right? So the attack surface against the kernel is a bit larger. Whereas in Chromium, the only attack surface you have is the actual these 5 system calls that you can execute: exit, close, read and write, and sig return. And the code paths of these system calls have been very, very well tested. Now, for both Qmail or the Chromium render process, you have this additional attack surface that restricts your API. So as a forward reference, and I think this is pretty much what you alluded to, confused deputies are still a problem. Do you know what a confused deputy is? Nobody watched shows from the 60s? The term confused deputy was created in the 80s when people first started working on compartmentalization, or the 70s even. Due to a show from the 60s where a deputy, like an officer in a small town, who's not very bright, put people into jail, but then didn't manage to lock the jail, or was often tricked into releasing people out of jail. Now, the confused deputy principle pretty much says that if you do have a trusted third party, the third party needs to be secure. If the third party is buggy, the privileged third party, you can make the third party do odd things that it shouldn't be doing. So for example, if this API that checks if you have privileges to do a special call does not do this check correctly, then you can do arbitrary things. Or if this third party has a bug, then you can make it do other things. But from a security perspective, compartmentalization requires that you find a bug in a trusted third party. Right? Even if you do get full code execution in the compartmentalized environment, right? If you get full code execution in the sandbox, in the Chrome render process, for example, so you have your first set of 2 or 3 bugs that give you full code execution in the sandbox, which is good, right? So you have some capabilities. You still need to find another set of bugs on the other end, right? So the only thing that code execution gives you in the render process is that you can set up the attack for the next stage. Without the sandbox, you could already launch arbitrary processes. So the sandbox requires you, or compartmentalization, by using isolation and least privilege, requires you to develop attacks that have multiple steps. So instead of requiring one set of bugs to exploit a system to trigger arbitrary computation or whatnot, you need a set of separate sets of bugs to go ahead. And if you look at current attacks against browsers, it's usually sets of bugs that are being used across the full system stack. So sometimes in a pwn-to-own competition, they are combining 5, 6, 7, 8 bugs across the different layers of the stack. Because of compartmentalization and because of isolation between components, they need to exploit a bug in a system, escalate their privileges there, get code execution, go ahead, go to the next component, trigger using the privileges they have in the first component, set up the environment to launch the attack in the next component, and then up and up and up until they get full code execution over the virtual machine monitor or whatnot. So in that sense, compartmentalization is useful to contain faults, but it itself is not a panacea. If it is itself implemented in software, it will have bugs. It will simply drive up the cost of developing an end-to-end exploit.
So is the difference between isolation and compartmentalization like the inability to escalate? Is that sort of the difference? Or?
Compartmentalization is isolation plus least privileges. Isolation is just the two processes that you have running on your system under your username, right? They are isolated from each other, but through the system call, the kernel does not restrict their interaction. Least privileges would be a system call policy that restricts how the processes can interact. Good question. Was that?
Yeah, that makes sense.
Okay, cool. Yes?
Sorry, maybe it's very obvious, but what exactly is forward reference?
A forward reference is, I will talk more about this later.
Okay.
So a forward reference, I'm referencing stuff that I will talk about later. Cool. I think in a book it's in one of the later chapters when we go into more, some more details. Exactly. Yes. Cool. Other questions? Right. So isolation by itself does not necessarily give you security benefits. Isolation is a stepping stone to implement stronger or better policies. If you want to do sandboxing, you need isolation, so you need to put things into a sandbox, and you need to make sure that they cannot just jump out of the sandbox. So these are the two sides. So compartmentalization combines the two sides and makes sure that this actually works. Cool. Next policy, one of my favorite policies, memory safety. Most of the bugs are due to memory safety issues on current systems. And memory safety is a property that ensures that all memory accesses adhere to the semantics defined by the source programming language. Or in other words, there's no undefined behavior. If you do access an object out of bounds, according to the C programming language, you're triggering undefined behavior. As soon as you're triggering undefined behavior, you're no longer executing under C semantics, but you've triggered a veered state, and you've turned your process into a veered machine, allowing it to do arbitrary things. Right? So veered machines, this is where all the dangers lie. Yes?
Correct me if I'm pedantic, but sort of, if I write a program in an assembly, is my program automatically memory safe by this definition?
Sure. If you write your program in assembly, you have no guarantees. Because in assembly, there's no distinction between integers and pointers. What you there was a project in the early 2000s. I'm blanking on the name at UC Berkeley on type assembly language that introduced or added types to assembly language to give some semantics to assembly level to enforce some kind of security properties. Somebody with Google open, just Google type assembly, let me know who did this. So this, you can give semantics to assembly code. You can then enforce additional properties on top of it. But it's very, very burdensome. Language or programming languages restrict you, right? They give you something to hold on to. They give you a memory model, they give you semantics, they give you expected behavior, they define how you interact with other components, how you break up large complex systems into other parts. For those watching the recording, the battery just ran out. The battery on the room microphone. They should do rechargeable batteries in those. Okay, cool. So the programming language gives you something to hold on to and gives you a way to abstract, and also gives you a way based on these semantics that you can prove or limit kind of behavior. So yeah. Other questions? Who was it?
Can you give an example for the semantics of a language?
For example, in C, when you're defining an object, right? Or the C programming language has pointers. And pointers are allowed to point to a given object. You're only allowed to access a point, you're allowed to increment a pointer, doing pointer arithmetic. As soon as the pointer goes out of bound, you're in theory not allowed to access the memory, right? Otherwise you would trigger undefined behavior. Undefined behavior is, by definition, undefined, right? So it can trigger anything. In another language like Java, the semantics would be that you get a reference but not a pointer, and therefore you cannot even create you cannot do arbitrary pointer arithmetic. Therefore, you could not create an object that is out of bound, an access that is out of bound. So the language restricts you to some extent, and we'll discuss more details in a bit about the different languages, if that's okay. Did anybody look up who the person on typed assembly was? Okay, don't worry. A tangent like memory safety is somewhat something odd, right? It's hard to define. It's also hard to have, and there's different kinds of bugs. The lack of memory safety can be used in weird ways to create abstractions, to create alternates, to change the state of the program. And I've talked a little bit about weird machines, and as soon as you start writing to arbitrary memory, you can rewrite the code, you can rewrite the data, you can rewrite other parts of the system. A quick example I have here is tool-assisted speedrun for those who are into gaming. Super Mario World speedrun, where Master Yan #3 created used an exploit to then do arbitrary code injection into Super Mario World through the controller, rewrite the game's memory, and then do now I have ads, holy shit. This is why I usually don't do tablets. Okay, cool. So we'll go cool assisted speedrun, and you see him doing very, very weird things, right? Jumping around, but all these movements, right? You're interacting through the game gamepad, and all of this changes state in memory, right? In the end, it's just a computer that has some memory, and he's writing bytes to memory by moving around and leaving state somewhere in memory here. Right? And it looks really weird what he's doing, right? He's jumping around, he's glitching, and it looks as if it doesn't make sense. But he's using this to set up the state of the game in a way that later allows him to have a very specific memory layout. And the memory layout then contains code that he can jump into. Right? So he's setting up individual bytes. The POW block can be used to then write individual bytes by triggering a given block spawning back and forth. So now he moved to a different area in memory where he's rewriting a couple of bytes that are then some kind of game state. And now, like, he rewrote the game to play Pong. Or Snake. Even with like collision detection and everything else, right? So this is quite cool. Let's see. No, go away. Okay. So one of the cool aspects here is that they did this in multiple stages. So the first couple of bytes are a very complex loader. Right? You've seen him jumping around and glitching and doing very weird things. The first 90% was writing the first 20 or 30 bytes into memory. Now these few bytes were just a small loader. And then in like 2 or 3 seconds you saw like a lot of stuff flying by on the right-hand side. So the very first stage was setting up arbitrary code execution, setting up a couple of instructions that then allowed him to loop and read in new bytes. So in the end, these 30 bytes that or these few instructions that he created by hand, by going back and forth, set up a loader, a very tiny program, that then looped and kept reading values, executable code into memory, and then at the end of this loop, by triggering the exit, he jumped at the beginning. So if you think about this, this is what a limited exploit technique actually is. It is very, very cumbersome to position and write individual bytes through an exploit, and he had to write a couple of 100 bytes. You don't want to write a couple of 100 bytes by going to specific positions and then doing frame precise jumping or whatnot. So he did this for 30 bytes, which encoded a loop that said, read in a character through the 8 buttons that can be pressed in a specific way. And then write this to memory, increment the pointer, read from the controller, write this to memory, go to the next until you send a specific end stream or finalize whatever token, and then you jump to the beginning and you're done. You had a question in the back, and then you.
Yes, I was questioning that how could you, like you have only 8 buttons and the byte goes from 0 to 255. How did you manage that you had only 8 possible bytes to write, one with every button, or there is like some?
So this was a tool assisted speedrun. Like you can encode. Like as long as you have one button you can morse. If you have 2 buttons, you have bits, and you it's a tool Yeah, it's a tool assistant speedrun. Right? The first link is a tool assistant speedrun. Here, the bonus, this is for you to watch on your own. It's about 10 minutes. I don't want to play it here. Like one crazy guy did this by hand. Right? Just as a quick heads up, like what he did is he first wrote a couple of bytes by like being the bug here is with the spawning of the POW block. You can trigger an arbitrary memory write. So and this is used to write 1 byte into memory somewhere. Like it's a memory safety violation. This is the memory safety bug. He used in the tool assistant speedrun. He uses this exploit to write the loader, and then use the loader to load the majority of the program. What he did is he used this bug to first patch the game that the number of coins gives you the hex value that you would be writing. So he patched the game with like 2 or 3 bytes to leak information. Right? Because we humans, we kind of suck at being frame accurate and pressing buttons at like 2 millisecond intervals. It's kind of hard for us, right? There's physical limitations, and our brain, our neuron signals don't transfer that fast, right? So what he did is like he used this exploit to trigger and change the game so that it would leak information on the coin number, and then use this to write individual bytes of memory. Watch the second one. He explains the exploit he did, and overall I think it's like an hour or so just patching the game.
Just to note on the controller thing, the SNES updates the controller bits every 60 times per second. You have 12 buttons on the controller. I believe this test used 4 of them, so that gives a throughput of 2,800 bits per second.
Yes, this is crazy.
It's like internet in the 90s.
Yes, pretty much. I unfortunately do remember those times. Thanks for the explanation. Yes. So this is pretty cool, the setup. But the point I was trying to make, right, is here there's initial bug, and if you're not careful, right, if you're not putting your attacker heads on, this bug may just crash your system because you're writing garbage, or not do anything at all because you're just writing garbage somewhere. Again, under an attacker model of a benign user, worst case scenario is it crashes the system. Now, if an attacker uses this bug, you're writing 1 byte somewhere. Right? The first step is that he wrote a couple of bytes that then encoded a small program that allowed him to load the rest of the program. And then he turned Super Mario World into Snake and Pong, right? It's a very odd way of doing that. And in the end here you see that there's the computational model depends on what the attacker does. Here, if you do have arbitrary writes, without any form of protection, so there's no mitigation whatsoever, it's very easy to get full control over the process. Cool?
There's some question.
Yes.
In this environment, we could execute the writable memory, right?
Uh-huh. So this is there's no separation whatsoever. There's no mitigation. There's no randomization. There's no defenses, right? There's no data execution prevention. There's no ASLR. There's no. It's a system from the 90s, right? It's yeah.
So basically, the way it works is that you can't write to the cartridge itself the game data, but
Right.
the way the CPU interacts with that is that it reads a section of RAM which is bound to that. But there's no protection, so you could just jump to a section of RAM which is writable,
Right.
which you might use to store,
Data.
how many lives you have left or stuff like that.
Yeah. Right. So you cannot obviously there's physical limitations, right? In your address space, if you have a given bank map or ROM bank mapped to a certain memory address, you cannot write to that ROM bank because it's read only. But if you can write to the memory, right, to the RAM, which is and then jump to the RAM. Right. Cool. Other questions? Very nice. you know what? Let's take a break here because this is a natural place to break. We'll see each other again. It's now 5 past. Let's do 20 past.